Hello everyone, this is Jim Corkins and welcome to Momentum. So we are starting with 4.0 and starting off, I want you to read Coletta Chapter 8 before you do the reading quiz. This content is related to Homework 10 for Physics 111 and Homework 7 for Physics 121. It's also related to Lab 10 and Lab 11 in your lab books. So what do we plan to do in what we're going to plan to study in Momentum in this entire module is momentum and impulse, conservation of momentum, specifically elastic and inelastic collisions, how momentum is related to energy, and we're going to kind of do some of that throughout this entire module. And then finally, we're going to do momentum in 2 dimensions. So the conservation of momentum, elastic and inelastic collisions, in this part we're going to just concentrate on 1D collisions. And then later on we're going to do 2D collisions. Okay? So here is some ideas of what is impulse and what is momentum. And we're going to get into that. But please read this in your PDF. And what is conservation of momentum. So here we go. Momentum basically is a property of all moving things. All objects have inertia, and momentum is specifically inertia in motion, right? So in a way, it's kind of an offshoot. It is actually a offshoot of Newton's first law. So often we talk about momentum and inertia as being a part of the same thing, as being almost the same thing. Well, specifically, momentum is inertia as something is in motion. Okay, so we're basically just concentrating on that, studying the consequences of Newton's first law. Okay, so how momentum is calculated? What is momentum? Well, it's a mass, and it's a mass moving, right? So it's a mass times velocity. Now, momentum is represented by the variable p, okay? So, and since it's made up of mass and velocity, its units are kilograms meters per second. Not kilograms meters per second squared, that's a Newton. This is different from that. This is momentum. It's just mass times velocity, so there's no squared s on the bottom of the denominator. So anything in motion has momentum, essentially. And this momentum can be positive or negative. Okay? So momentum can be positive or negative. Since it's got a mass times velocity, the direction of the velocity vector, left or right, negative velocity or positive velocity, will determine whether or not it's got a positive or negative momentum. Okay, mass is going to always be positive, so that actually mass is unitless. It's directionless, I should say. It's just a mass. It's just a number. Okay. So it's important to note that an object at rest has no momentum, but it still has an inertia. It has a resistance to move. Okay. So that's the differences between momentum and inertia. Inertia is specifically an object's resistance to its current state of motion, whether it's moving or not moving, right? Momentum is an object in motion, and that's what we're looking at. I had mentioned impulse before, and we'll talk about impulse in a second, but here's how the two are related. So when an object has motion, so an object is moving to the right, and in your force diagrams, you had done force diagrams where two objects were interacting with each other, right? So let's say I'm going to use the markup tool on the comments. So we had done problems where you had a box up against another box, right? Right, and so since they're touching, the block on the left is going to feel force to the left. The block on the right is going to feel force to the right. And this is left, right. And this will be positive FLR, right? So these two blocks are interacting with each other. Well, how is momentum related to forces and impulses impulse? Okay, I'm getting to that. So suppose the block on the right, and I'm going to give this an R and this an L. Okay, so this is block R and this is block L. Well, suppose block R has momentum, meaning it's got a velocity vector and it's got a mass, so it's got a momentum to the right. Well, the moment that these two blocks hit, okay, right here is the moment that they are going to be exerting a force on each other, okay? So when you study impulse, you could study impulse of an entire system, and you could study an impulse of an object. And what I mean by impulse is a force times a period of time, okay? So as block R is then touching block L, right and left, and I labeled those backwards. Sorry about that. As block R is touching block L is pushing block R to the left, so it's going to have a negative force vector, right? Correct? Okay, it's going to be pushing it to the left. So while it is actually hitting it and block L is slowing block R to a stop over a period of time, that force that block L is applying to it, slowing it down, right? It was moving to the right. Now it's got to be slowed down by a force applied to it to the left over a period of time, right? Over delta t. Well, that force in that time accounts for this block's change in momentum from going from a state of moving to the right with a positive velocity and thus having a positive momentum, and until finally, and let's say block L is stapled in place, so it's not going to move. So now after the two hit, block R is going to now come to a stop, and now it's since its velocity is 0 and momentum is mass times velocity, then its momentum will be 0. And let's say there's like some sticking agent, and so block L brings it to a stop, right? Correct? So what does that mean? Well, that means what impulse is it's a force applied to an object or a system actually over a period of time. In fact, it's the net force applied to that object. So we're just looking at block R. It's a force is going to be applied to it opposite the direction of motion, bringing it to a stop, okay? And so that's a net force acting on that object, right? Correct? And let's just do a little itty-bitty force diagram here. I'm going to go ahead and move this delta t here. And so it's got an mg down, it's got a normal force up, and it was being accelerated to the left because it was being slowed down at the time. So essentially, here's what I'm saying, is that impulse, which is the variable j, is equal to, in this case, and this should be just an arrow, is equal to an object's net force times its over a period of time. So the net force applied to an object over a period of time. it is also equal to an object's change in momentum. Meaning an object's change in momentum is going to be mass times its initial mass times final velocity minus mass times initial velocity, right? And those are vectors. And this is a vector, your J guy is a vector, and your momentum is a vector, okay? So that in altogether is what is impulse and momentum, and that's how the two are related, and that's how impulse is related to momentum is through a force over a period of time, okay? So you could see that force diagrams are still going to be important to understand when we're doing analyzing an object's momentum and impulse. So basically, here is the summary of that, right? You have impulse, which is a J vector, which is equal to force times, it's the net force over a period of time applied to an object or system, which is equal to the change momentum for that object or system, which is then finally equal to the difference in momentums from the initial to final, okay? So the consequences of impulse is this: if you apply a force, so if you apply a force, let's talk about what the consequences are, okay? So if you have force, notice that force times time is equal to change momentum. So I'm going to take the change in momentum and divide it by change in time, right? So there's these two relationships right here. F delta t is equal to change in momentum Okay, so what this first statement is saying is a brief force applied over a short period of time interval produces a small change in time. So what they're saying is if you apply a brief force, a small force, over a small period of time, you will have a smaller change in momentum, right? Since these are all on the numerator. Okay, and so this is that first part right here. The second part is saying this. If you push with twice the force, if you push with the same force over twice the time, a large period of time, you're going to produce a twice the momentum change, right? So that means the object will have a small momentum in the beginning, and now it will have a very big change in a very big final momentum, right? But also over here, I divided, you have force times time times change time is equal to the change in momentum, right? So I divided both sides by the change in time. And now I'm using this to illustrate how force has an inverse proportion to time and related to change in momentum. Okay, so there is an inverse relationship between force and time when we're talking about the change in momentum. And we'll get into that right now. Okay, so I'm going to go ahead and change this black, and we'll talk about it. So if you ever, when you're a little kid and you jumped off the swing set, and you would, maybe the first time or two you jumped off the swing set, and you landed with stiff legs and how it really hurt. And it almost felt like your bones rattled, right? And then maybe you realize, like, hey, if I crumple to the ground or I roll after I jump off the swing set, it doesn't hurt as much, right? Well, that's what we're talking about here, okay, with this inverse proportion, okay, to time and momentum, to the change in momentum, right? So in both cases, when you're jumping off the swing set, you're going from a state of moving to not moving, right? And I'll illustrate that here. I'll actually draw the mass times final velocity minus mass times initial velocity over the total change in time, right? So in both cases, you went, when you jumped off in the air, okay, so you're a little guy, and you're now falling, so you're now falling down, so you have a negative initial velocity, and what that means is you also have a negative initial momentum, right? Well, now you fall on the ground, and your little mouth's open and you're not feeling too good. So your velocity and your final velocity and thus your final momentum are 0, right? Well, in both cases over here, since we're using this equation right here, in this particular case, your final velocity is going to be 0. Oops, and I just want to change the color of that. So in this particular case, your final velocity is 0, and your initial velocity is negative, right? So I'm going to do some erasing here too. I'm going to use a black pen. And your initial velocity is negative, right? So it's going to be minus a negative initial velocity, right? So in both cases, your overall change in momentum is just equal to mass times initial velocity. I should do a better job in slowing down writing that, right? So your total change momentum is just mass times initial velocity over the change in time. Well, if we look at this information right now, what brought you to a stop? Notice that this is going to result in a positive force, right? So that means the ground pushed up on you with a force, and that's actually the normal force pushing up on you, right? Because you, again, you're being accelerated upwards, right? And this force is actually going to be the normal force pushing up on you because it's a surface force, right? I should draw that. I'll mark it here. So this is the normal force, right? You're falling to the ground, and then you finally hit the ground now, and you have a small mass times gravity down, right? So when you sum the forces in the y direction, you get a normal force up, a mass times gravity down equals mass times acceleration up, right? So your normal force, which is equal to the force of the ground pushing up on you, which is slowing you down, is going to be equal to mass times gravity times mass times acceleration, right? So that's going to be this part, right? mass times acceleration plus mass times gravity, right? So here's what we're talking about. So in both cases, your change in momentum is mass times velocity, right? But as you hit the ground over a period of time, I'm actually going to just call this, I'm just going to call it the normal force just to keep it simple. That force, which is the normal force, that force which we determined is actually just the normal force, is equal to, and which is equal to mass times acceleration times mass times gravity, okay, is equal to the change of momentum, which is mass times initial velocity over a period of time, right? So if you fall and land stiff-legged, and here's the point of this, I'm finally getting to the point, is this, that if your change in momentum is a small period of time, then your change in force is a large period of time, then your change of force is going to be very small. Your force is going to be small applied to you, right? So this force, which is the normal force, right here, okay, that's the normal force, okay, is going to be small, right? So when you jumped off the swing set and you crumpled your legs, you were increasing the amount of time that the force was changing your momentum. So by increasing that time, you are lowering the overall force being applied to you. Okay, you were changing the overall force, and that's because you're actually changing this acceleration. Your acceleration was maybe large. If you land stiff-legged, that acceleration is going to be really large, right? But if it's, so this is stiff-legged, so stiff. But if your acceleration is small, so you crumple, and I'll just call that crump, your acceleration is going to be really small, okay? Which in turn is going to increase, a lower acceleration is going to increase the time of impact, right? Which is then going to lower the amount of force being applied to you. On the other hand, if you land stiff-legged, so if you land stiff-legged, I'll have to replace all those. By landing stiff-legged, you're lowering your time of impact. And by lowering your time of impact, that's going to increase the acceleration. So it's going to have a larger acceleration, which now is going to increase the acceleration here. Since your mass times gravity isn't changing, then that's going to increase the normal force, which is going to increase the force of the ground applied to you. Again, this is the normal force in this case, okay? So by doing that, you're by elongating the period of time, you're lowering the force being applied to you, and that's because the acceleration is being lowered, right? The acceleration vector magnitude is actually decreasing. The magnitude is being scrunched. That vector is getting smaller, right? But if you land stiff-legged, well, that change in momentum is going to happen over a very short period of time, which is going to increase the amount of force being applied to you because the acceleration is increasing, right? If you go from a moving vector to a zero, a large velocity vector to a zero velocity vector, well, that change in velocity occurs over a period of time, and that is the acceleration, right? Well, there's like really cool, there's some cool problems that get that this applies to, right? So and I ran across this problem in another physics textbook. And this is a problem like, if you have a chance, if you're driving along, mind your own business, and like maybe a kitty cat jumps out in front of you, and you have the choice to run your truck into a brick wall or run your truck into a haystack, right? Which one are you going to choose, right? Both cases, the initial momentum is going to be, you're initially driving, minding your own business. So this is the initial momentum of both things. And they're equal, right? And in both cases, the final momentum is going to be 0, right? And what they're showing here is this. Just like the last problem, since change in momentum over the change in time is equal to force, right? In the haystack's case, you are increasing the time of impact, right? So in both cases, the change in momentum is a constant. I should illustrate that right here, right? You're both going from the same initial velocity to the same final velocity, which means you have the same initial momentum, and you're going to have the same final momentum, right? So your change in momentum is going to be same in both cases. But when you hit hay, that change in momentum is going to occur over a large period of time, right? Which then in turn is going to decrease your acceleration, right? Force is equal to mass times acceleration. It's going to decrease your amount of acceleration, which is then going to decrease the force on you. Over here, with the brick wall, you have the same change in momentum as before, right? But now your change in time is going to be very small, which is going to make you have a higher force, and that is because your acceleration is going to be really big. You're going to have a large acceleration, which in turn is going to have a higher final velocity, right? If your change momentum, so again, I just want to illustrate that final velocity minus initial velocity over a period of time is acceleration, right? So if this change in time, both cases you're going to have the same change. In both cases you're going to have the same change in velocity, right? But again, if you have a small period of time of impact to go along with the brick wall, that means you're going to have a high acceleration, right? And then if you have a high acceleration, then your mass times acceleration is going to be high, and that is the force. That's the net force on both objects, right? So that's how force diagrams, that's how forces and acceleration influence change in momentum to create this thing called impulse, which is the J vector, which is J. And I'll put J here again to remind you. This is J. Okay. So we talked about how you could look at the change of momentum of an entire system, or you could do a change of momentum of an object, right? And so this is to remind you, this slide here is to remind you that these momentum, initial momentum, final momentum. So initial momentum final momentum are both vectors, right? And the difference of those two vectors is the j vector, okay? So you could do vector subtraction here, right? So it starts off with an initial momentum. This line right here is an initial momentum down to the right, okay? And then you're used to vector addition. Well, this is vector subtraction, right? And then you have a final momentum later on over here, which is kind of pointed, actually I should say a little up and to the right, and that's the final momentum vector, right? Well, when you subtract those two, right, if you added that, it would look like this, actually. It would look like this, and then down to the right vector. So this is positive f, it's pointing to the right. This is positive p, the initial momentum, right? And so the j vector is going to be, this is not the j vector, right? You have to reverse one of those vectors, or you have to do it like this. I like to reverse one of the vectors. So since we're going to, since our initial momentum vector is pointed down and to the right, and that's a positive, right? Correct? Well, a negative of that is up and to the right is going to be the negative initial momentum vector, correct? So by adding that negative initial momentum vector to that positive final momentum vector, so you're now doing vector addition, the difference there is going to be this, p final minus p initial, which is the j vector, right? The j vector is the change in your momentums, right? And so that's the difference between the two, okay? And that's how they got this. I kind of don't like doing vector addition this way. I like reversing one of your vectors and then vector addition, right? So this makes more sense to me. So just I want you to make sure that you're thinking about these objects as in terms of vectors, okay? Well, let's talk about what is happening during that time where an object is going from not moving, right? So we're gonna do the impulse of the soccer ball, right? So this graph is supposed to represent the soccer ball, okay? So this soccer ball is starting off with a momentum, with an initial momentum of 0, right? Which means its initial velocity is 0. If somebody says your initial momentum is 0, that has to mean that your initial velocity is 0. Okay. Well, now this foot is now going to start pushing it. So it's going to apply a force. It's going to apply a force to this guy, right? And we'll say this force is a constant force. Well, this force is, the foot is now hitting this, okay? I shouldn't say it's a constant force. Maybe it was a smaller initial force there. Now the force is being maximized, and now the force is decreasing over time, and that's because the ball is being reformed, okay? So this is at t equals 0. This is 0 seconds, and I think this right here is actually, this is occurring, I should say, at the, this is occurring at the 30, I shouldn't say 0 seconds, sorry about that. So this time is occurring at 30 milliseconds, which is 0.3 seconds. Okay. And this is occurring when it's got the max force on it right here at the 0.50 seconds mark, or 50 milliseconds mark. And then finally, the ball is now leaving the foot, and this is occurring at the 0.70 seconds, right? So this occurs here, this occurs here, and this is occurring right as it's in contact, okay? And what we'll have also is now it's going to have a final momentum that is going to be positive, okay? So basically, the ball is starting to move right here, okay? It's still not moving right here. So this is kind of interesting. Balls are an interesting object. So here's where the ball is first, the foot is first contacting the ball. So it's applying a small force at time 30 milliseconds, right? So now the ball is initially not moving. Even though the foot is pushing on it, the ball is actually squishing down and getting squishy, right? But the ball's not moving. And even here you could see the ball is not moving. Look at where this is related to the picture. Here's the center of the ball. And notice that is the same position in the picture as about, oh, sorry. Well, it's about, it might be almost not moving. Anyways, my point is this ball is first being kicked and it's squishing down. And as it's squishing down, it looks like it did move to the right a little bit. So the center of that picture was right here at in the beginning, and then notice it moved to the right a little bit. And so now the center of that picture was here, and now the ball is way over here. So the ball basically started getting kicked as it's being the foot is being applied to it. Its initial contact, the ball is squeezing down, and then it starts to move to the right a little bit. It does look like it's moved to the right a little bit in this next picture. And at this next picture, now when the ball is beginning to move at this point, it's at its maximum, it's squished, the ball is squished down as much as it can, and it's now going to start moving, right, to the right. And so now the ball's moving, the force on it is at its peak, its maximum, okay. And now the ball is going to be unsquishing itself as it's moving to the right, and that force is dropping. So this is the context of that, right? Well, we've done calculus before, all right? And so what we have learned is that if you integrate a force over a period of time, an integral is the area under the curve, right? Right? So that area under the curve, which is this entire thing, this entire red area, is the area in the curve. Well, that area under the curve is equal to the change in momentum, which is actually the J, which is actually the impulse, the J vector, okay? I put some YouTube links to this, and so what I'm going to do is show you what is really kind of going on during an impact, okay? So here's that first link, and this is going to be a link where you're going to see a golf ball being is moving to the, it'll be moving to the left, so it's going to have an initial momentum to the left. Now, when it hits this plate, the plate is going to bring it to a stop, which means it's going to apply a force to the right. And then you're going to notice the ball gets squished down. Okay. And then the ball is going to start to reform back into the ball, back into a ball form. It's going to squish like a pancake. And when it reforms, it's going to be coming off the wall to the right. So now the wall is almost going to give it like, it's almost like a second force to the right. The first force is to bring it to a stop. Then the first rightward pointed force is going to be bring it to a stop. In a way, it's going to kind of give it a second force to speed it back up to its original incoming speed, but now pointed to the right. So the change momentum of an object that hits a wall and comes to a stop, or hits something comes to a stop, is actually going to be the change momentum is actually going to be small in comparison to it bringing it to a stop and then pushing it back out the way it came. That's going to have a larger change momentum, and so that means it's going to have more force on it. Okay, so this is, I'm going to try talking about it. It's going to be coming left, and notice it brings it to a stop and it turned into a pancake. Well, now it's going to be forming back into a golf ball, and it's going to then have a momentum to the right. So here it's got an initial momentum to the left, and now it's just touching the wall. And that wall is going to be applying a force to the right. Okay. To bring it to a stop. And I can't believe golf balls do this, but this is a really fast golf ball. And this golf ball changes into a pancake and is brought to a stop. Okay, so now its momentum is 0. Well, now it's going to start reforming into a ball, and now the wall is going to push it to the right again, giving it a force back out the way it came in with something close to its incoming speed. Okay? I can't believe balls do that. So interesting. The second video I have on here is basically it's by Ping, and it's about how they actually are making how they make golf balls, and these people understand momentum and impulse very well, and basically that is a lot of golf. That is all of golf, really, is momentum and impulse. Okay, especially when you're hitting the ball, that is. Okay. Well, this is the timeline of what is happening. Okay, so when a ball comes in, so when that golf ball was coming in this case it's going to be pointed to the right. The golf ball comes in, the wall hits it. The wall is applying a force to it, bringing it to a stop. And then it's going to be pushing it back to the left with the same speed, or close to the same speed that it came as it was coming in, right? This is the initial momentum. This will be the final momentum, right? Notice it had a rightward pointed initial momentum. The force applies to it to the left, and thus afterwards its final momentum is going to be to the left as well if it bounces off. Okay? There's a cool approximation that you could do. So this is, if I asked you to get the area under curve of this is going to be really complicated, right? But there's a really cool approximation. What you can do is, if you take the initial force at this point, oops, I got to go back to markup. And I'm going to do this here. If you take the initial force and the final force, and you take the averages over this entire thing, right? if you take the averages over this entire period of time, okay, the average force over this entire period of time, you could approximate this shape into a square, or a rectangle rather, okay? And getting the area under the curve of this rectangle is a lot easier, right? It's just length times height, right? Or delta t times f average. It's much easier than getting the area under this entire weird curve, right? So if you find the average force across this entire shape, okay, you could actually get that average force over the same period of time is this shape, which is actually just the impulse, right? So it's a cool way to change something that's a complicated integral into something that's quite easy. Okay, so in the in-person labs, what you would do is just find the just highlight this entire area and find the average force, right? In graphical analysis, and as well as I think Tracker, and as well as Logger Pro, you could just do the integral of that shape. There's little tricks to doing the integral of this shape too, okay? But there's a couple homework problems where they give you the average force over the period of time, and they give you this shape, but they said this is the average force. Well, just know that if you're given the average force, that is the same thing as this, okay? They're the same area. So let's do a problem that applies everything that we've learned, and actually it'll apply some things about the nature of momentum related to velocity and mass, okay? So this is a really cool problem. I'm going to get ready to mark it up here. So this is how you mark it up. You hit the comments button. You go to the little pencil. Okay. All right. So we have a force of 200 newtons that acts on a 100 kilogram boulder, and we have a force of the same magnitude that is acting on the 130 gram boulder. What is that? That is 0.13 kilograms. So the boulder is about 220 pounds, and this pebble is just, it's a small little guy. So we're being asked, given this force and these two different objects, how does the change in a boulder's momentum compare to the change of the pebble's momentum? So I guess what they're saying, is a boulder's momentum greater than, less than, or equal to the change in momentum of the pebble? So go ahead and take a moment and try to answer this question for yourself, okay? And try to use all the stuff that we were doing before to try to answer this question and give it your best shot. So hit the pause button now. Okay, well, whenever I see force, kilograms, and momentum, the momentum, I think mass times velocity, and that's momentum. Okay, and this is weird. I'm going to get that out of the way. So I'm just kind of writing equations that I think I'll need. And I know since there's force and momentum in the same problem, what I do is I think of impulse, which is F delta t. I've got to put the little vector heads on my stuff. Is equal to the change in momentum. Okay? So let's think about this for a second, okay? You're going to apply a force to a little grain of sand. And then you're applying the same force to a big boulder that is much bigger, okay? So the same force, and over the same period of time, okay, so they're having the same period of time, right? So the same force is acting on both objects over the same period of time, and they're basically saying who's got compare the rate of change of momentum. So what I'm going to say is this. I'm going to put it in context. You're applying the same force over the same delta t for both objects, right? And let's say this initial object, even though it's got let's say they were at rest at the beginning, correct? Let's just do that. So that means no matter what, their initial momentums are the same. They're zero, only because their velocity is zero. But after that force is applied, they're going to have a final momentum, right? And this guy's final momentum is its itty-bitty mass times its velocity, okay? And this guy's final momentum is going to be its large mass times its final velocity, right? Well, if they have the same force times change in time, so if they both have this, I'm going to write this together here. If they both have the same force applied over the same period of time, and that momentum is going to be mv final minus mv initial, and both objects have the same initial momentum, then that means both objects are going to have the same final momentum, because f dot t delta t is going to be equal, right? Is going to be equal for both objects, right? So that means the final momentum here is going to be equal to the final momentum here, since they have the same force in the same period of time, and both of them have the same initial momentum of zero. Okay? Regardless of what their initial momentums are, if they have the same f and same delta t being over the same period of time being applied to them, their change of momentums are going to be the same, right? So I'm choosing C. Okay, well, let's see what this says. They said it is correct. It is equal to, and the rate of change in momentum is in fact the same force, so that means they're going to have the same change in momentum. So our reasoning was right. It was correct. Cool. Well, now here's the same problem, but now what they're saying is compare the two guys' velocities. Okay, so the same force, again, I'm going to redraw this. You have a little pebble with a force of 200 newtons being applied to a little pebble, and that pebble's mass, again, is 0.13 kilograms. And then you have the same force of 200 newtons applied to a huge boulder. Okay, and this guy's mass is 0.13 kilograms, and this guy's mass, is a big guy, it's going to be 100 kilograms, right? Okay, and let's say they were both initially had not moving, so their initial momentums are going to be zero. So let's try this. Okay, let's give a time period for the impact. Let's say both impacts, since they're also the same, take place over the period of time of 1 second. Let's make the math easy on us. So what I'm also going to do is try to reason through this problem before I run to the equations. Okay, so after the impact, so this is prior to the push. The final momentum, we know from the last problem, is going to be the same, right? This guy right here, this little pebble, is going to have a momentum vector to the right, a final momentum to the right, and this guy is going to have the same final momentum vector to the right. Okay? But does that mean that their velocities are going to be the same or different? I don't know. Let's find out. Let's think about it for a second. If their two momentums are equal after the impact, right? But this guy's got a small mass, right? And we know that mass and this momentum is equal to mass times velocity, right? Well, the momentum is constant for both cases, right? But let me write this in a place that we could see a little bit better. But we know the momentums of both objects are going to be the same, right? So that is just a constant, so that doesn't matter. But let's think about it for a second. If you got a pebble, so you're going to have a small mass, in order for you to have the same momentum as a larger object, you have to have a higher velocity. So I'm anticipating that its velocity vector for this guy is going to be huge. And the weird part about this too is, well, if you've got a larger mass, right? I'm going to do a analysis on this. That boulder has a much larger mass, so its mass is huge, so it's going to have a much smaller velocity. So I'm predicting that its final velocity is going to be small. Well, there's a way to do all the math all together, right? So I'm going to start out going F delta t, just like I normally do. And that's equal to the change in momentum, which is mv final minus mv initial, right? And we know that the initial velocity, these two objects were not moving, so the initial momentum was 0. Well, afterwards, the final velocity is what we're going to try to find. So we need to divide both sides by the mass, and we have that final velocity, right? Well, let's do the pebble first. This is 200 newtons times 1 second, so that's going to be 200 newton seconds over 0.13 kilograms. Well, the final velocity of that guy is going to be, was that 200 newtons times 1 second divided by 0.13 kilograms. That is 15, oh geez, that is a big number, 1,538.46 meters per second. Wow. Just make sure I got that number. 38.46. 38.46 meters per second. That is the pebble's speed right there. The boulder's speed is going to be 200 newtons. Again, same force, same period of time. Impact is, the delta t for the impact is same period of time. And this is 100 kilograms. Well, 200 newtons times 1 second over 100 is going to be 2 meters per second. So that guy's final velocity is going to be much smaller. Okay? So what we're going to say then is that the boulder's final velocity is going to be less than the final velocity of the pebble, right? Much less, 2 meters per second compared to 1538. And we're right. So our reasoning was really good on that. Okay? Well, let's do one last problem. Actually, there's a couple more problems to do, but this is a really good problem. And the basic problem is this. You've got a person standing under an umbrella. Okay? So here's their umbrella. And I'm going to have another umbrella here. And you've got, its umbrella is in a rainstorm. So you've got a drop of rain right here. It looks like a little guy with a hat. And it's got a velocity down, right? So it's going to have a negative initial velocity, and so its momentum is going to be negative. And the rain will turn to hail later. So this is a later case. I'm going to draw hail. kind of looks scratchy. And we'll say this, both the masses are the same, right? They have the same mass, and they have the same initial velocity. So that means their initial momentums will be equal to. Okay, so we'll just keep it the same. Same mass, raindrop has the same mass as a hail, and they both are traveling at the same speed down. Okay. However, I think what this saying is that this guy, the little guy here, the raindrop is just going to get splat, which means its final velocity is going to become 0, and thus its momentum is going to be 0, right? I think what they're saying is that I've held basically hail bounces. Okay, so let's say now afterwards the hail has bounced, and now it's traveling up with a positive velocity equal to its initial the positive speed equal to its initial speed, and thus if its initial speed is equal to the final speed, we'll just call them both the same velocity, right? They're the same speeds, and I'm drawing little magnitude lines there, right? So that's this case only. Okay, so that means its initial velocity, its initial speed down is going to be equal to its final speed up, and that means the magnitude of its momentum down is equal to the magnitude of the momentum up. It's bouncing perfectly off the surface of the umbrella. Okay. Well, which is going to require more force to hold the umbrella? So let's say this: both impacts occur over the same period of time, and we'll just call it 1 second just to make the math easier. Okay. And we'll say this, that the initial speed down is going to be 1 meter per second. And so that means all these magnitudes are going to be the same. So even though it's two different objects, they're going to have the same speed down. So this speed is equal to this speed down. The masses are equal. Okay, so that's pretty much the setup. So the question is which is going to require more force to hold the umbrella up? Well, let me think about this for a second, right? Because when we're talking about the golf ball and the wall, when the golf ball hit the wall had to change its momentum to 0, right? To bring it to a stop. Okay? And so I'm going to draw the force with a different color. And so that means it had to apply a force upwards to bring it to a stop, which is what's happening with this rain case, right? However, in this case with the hail, the hail drop is coming down. It's going to hit the umbrella, and the umbrella has to bring it to a stop initially. But then it's got to apply a second force upwards to speed it back up to its original speed upwards now. So I'm thinking it's going to have to be twice the force than the hail. The hail is going to require just a force to bring it to a stop, while the raindrop is going to require just a force to bring it to a stop, while the hail is going to require a force to the same force to bring it to a stop, but then a second force to speed it back up to its original speed. So in a way, it's kind of interesting. You got to think of it as two different forces. Okay, well, let's let the math do it. Okay, well, the change of momentum here. Actually, I'm going to do the initial equations here. Both objects have a force in the same period of time. Both objects are going to have a final momentum. Well, actually, no. Both objects have an initial momentum, but one of them is going to have a final momentum. So basically, to do this, I've got to divide the change in momentums of both objects divided by the time of the impact. Okay? So let's do the raindrop first. The raindrop has an MV final, and that is 0, and the MV initial there. And the time of impact is going to be 1 second, right? And the MV initial for both objects, final, is going to be negative right? So what I'm saying is this initial velocity is a negative number, right? Which is, and I should just put delta t here just to keep my equations, right? So both objects have a negative velocity downwards. So that means it's going to have a total momentum of mv initial over 1 second, right? And that both have the same mass and same initial velocity, right? So this guy's force is mv initial over 1 second. Well, let's try to find the other one. Well, this is mv final upwards minus mv an initial velocity downwards, okay, over that 1 second. And I want to revisit this, since initial velocity is equal to velocity, which is 1 second. This is just mv over 1 second, okay? Well, mv final is upwards, and we said that v final is equal to v, so that's going to be upwards. It's got the same speed as the incoming speed downwards. And this is going to be plus mv downwards, right? Negative times negative, positive, over 1 second. So basically, this is going to work out to be 2 mv over 1 second. Interesting. This guy, the raindrop is 1 mv over a second, and the hail is 2 mv over a second, which means that it's got twice the force on it, which means we're correct in our reasoning. It's going to take twice the force to hold up an umbrella during a hailstorm than it is during a rainstorm, as long as the initial velocities are the same coming down and the initial masses of both objects, of the rain and the hail, are the same. Pretty cool. So basically, this can be applied to this. Anything that sticks, if you throw something and it sticks to a wall, that wall had to do less force to bring it to a stop. But if you throw a bouncy ball across against a wall, it's got to bring the bouncy ball to a stop, but then it's got to speed it back up to its original incoming speed. So it's got to apply twice the force. So that's going to be a bigger impact, right? It's going to be a bigger force. Cool. Cool. And we're right. It's going to take more force to hold up an umbrella while it's hailing. Well, now I want to move on to the overall tactics and how you should approach these problems, right? So whenever you read a prompt or a multiple choice question or a problem, try to go ahead and sketch the situation, right? And as you're sketching the situation, you should be putting in a coordinate system of some type, right? So when I was sketching doing my sketches, I'll go back to it and show you. I had, well, when I was sketching my problems, all the down vectors, all vectors, velocity vectors, momentum vectors, and force vectors, which were pointed down, are negative in the negative y direction. Any vectors pointed up will be pointed in the positive y direction, so I labeled them positive. Any vectors pointed in the positive x direction, I labeled positive. Any vectors pointing to the left in the negative x direction, I labeled with a negative. Right? Once you do that, once you've got your situation sketched and you've drawn your vectors and labeled them with your velocities, make sure you subscript them with initial and final. Also, be careful about the masses. If something's got twice the mass of another, just put 2m or just 1m, right? So try to subscript or try to use, or I used capital M in one case to draw like a larger mass object in the case of the boulder and the pebble, small mass. And so what you're also going to do is what you should be doing is also be listing out the given information, which is what I was kind of doing. I would start drawing out the equations and stuff like that. But what we're going to do now is we're going to add into this, besides listing the information and identifying the unknowns, we're going to draw momentum bar charts. And momentum bar charts kind of help you identify the positive and negative momentums, but also kind of helps you build your equations, right? So let's go ahead and do that. So here we have the first problem, and this is, I'm going to try to train you on how to do momentum bar charts using an actual problem, okay? So we have an object, we have a ball of mass m that is traveling at negative 30 meters per second to the left, okay? It's going to hit a wall, and it's going to bounce off the wall at 20 meters per second towards the right, okay? And you're being asked to find what is the impulse, what is the j vector. So we're going to use this momentum bar chart to show you how to do the training of that, but also show you, anyways, on how to build that, but also how to find the impulse, okay? Let us begin. I'm going to mark up this document. So what I'm going to do first is our unknown. I'm going to list out what our knowns are. Well, we have the mass. That's weird. We have the mass of the object, which is 0.4 kilograms. We've already got a sketch. We don't need to draw that. We have the initial incoming velocity of negative 30 meters per second to the right. We have the outgoing velocity of 20 meters per second to the right, 30 meters per second to the left, I meant. When this hits the wall is going to produce a force. And it's got to produce a force to the right because the initial velocity is to the left. So for it to slow it down, it's got to push it to the right to bring it to a stop. And then it's got to apply an extra force to get it back moving out to the right. And so this impact is going to occur over a period of time. And that is our j vector, okay? So we need to find what the j vector is, okay? So we read our prompt. We have a diagram that is supplied to us. We listed out our variables and listed out our unknowns. We don't know f and t, f delta t, but we don't care. We're just finding the j vector, and that's what we're being asked to do, okay? Well, here's what a momentum bar chart is. Okay, we're gonna list out the initial momentum coming in, right? And so the initial momentum coming in is mass times velocity, right? Which is going to be 0.4 kilograms times negative 30 meters per second, right? And that negative is going to make it have a negative momentum, okay? So 0.4 times 30 times negative 30, so that's going to be 12, right? So this is going to be, this initial momentum coming in to the left is going to be negative 12 kilogram meter per seconds. Okay? The momentum out, the final momentum to the left, is going to be 0.4 kilograms times 20 meters per second, right? And that final momentum was at 80, so what is that, 8 kilogram meter per second? Cool. I probably could have done that in the head. Anyway, so let's look at the momentum bar charts, right? So here's what we're saying. Basically, this thing is going to have a negative momentum. Initial momentum is going to be negative, and it's going to be negative at about what we think is about negative 12 kilogram meters per second. So that's what that's supposed to represent. Afterwards, it's going to have a positive momentum at the rate of about 8 kilogram meter per second. Okay? So this bar chart is actually representing our equation, right? J vector equals momentum final minus momentum initial, right? The force F delta T equals the change in momentum. And so what this represents is the initial momentum plus the final plus the impulse is equal to the final momentum. So that's what this bar chart represents. It's the initial momentum, right, plus the impulse is equal to the final momentum. What this is saying is this stuff, the initial momentum plus the impulse, should be equal to the final momentum. Okay? So that means you have negative 3 blocks here that has to, or negative 12 rather, I should say that. These 3 blocks represents negative 12. This one block represents positive 8. Well, how do you get negative 12 kilogram meter per second to be equal to 8? Positive 8. Well, you have to have, well, let's take a look at this. Well, this force is to the right. That means the J vector is also going to be to the right as well. That force times time is equal to the J vector, and that's going to be to the right. And in order for this negative 3 blocks to be equal to a plus 1, we've got to add 4 blocks to this, right? And these 4 blocks has to make this negative 12 become a positive 8. Well, how do you do that? Well, you have to add 8 plus 12 to this, right? You got to nil out this. You got to add 12 to this negative 12, plus you have to add 8. So basically, you have to make this 20 kilogram meters per second, right? So you basically have to nil out that negative 12 by adding 12 to it, and then add an 8 to it, right? So this J vector is 8 plus 12, or 20 kilogram meter per second. So 20 minus 12 should be equal to 8. So I'm guessing that this is going to be a positive, so this is a positive 20 kilogram meter per second, which means that is going to be to the right. Okay. That's what I'm guessing. Let's just copy this to an equation form, right? Well, this is 12 kilogram meter per second plus our J vector. Let's say we didn't know it yet. That's going to be equal to 8 kilogram meter per second. We're going to add the negative 12 kilogram meter per second to both sides. and that's going to be equal to 20 kilogram meter per second. To the right. If it's positive here, the j vector is positive, and I hope so because the force has got to be positive, so this is going to be A. So this is how you use, so let's just check to see if we're right, and it looks like we are. So this is how you use a momentum bar chart to actually help you plot out and understand what is going on as far as the momentums. Okay? Well, let's go through that whole process over, right from the beginning to the end. Okay? So what we have is we have a rocket sled coasting at 20 meters per second. So we have a rocket sled. So I'm going to draw the little rocket. Okay. And it's 500 kilograms coasting to a stop. So it's got a velocity to the right. It's got an initial velocity, and I'm going to set it to the right. And so it's going to have an initial momentum to the right. And this is a mass of 500 kilograms. And it's got a velocity of positive 20 meters per second. Okay. It then turns on the rocket engines. Okay. So over here, so that's the initial case. Now it's going to turn on the rocket engines, right? Okay, and the mass is still 500 kilograms. And it's going to turn on the rocket engines, and the rocket engines are going to give it a thrust, which means it's going to push it and I'm going to do this. So I'm going to draw the rocket over here, so that way I could draw a force vector pushing on this too. And I'm going to draw the force vector in terms of a red vector. So there's going to be a force added to this, thrusting it, giving it a thrust to the right of 1,000 newtons. I'm trying to list my variables here at the same time. And what should be the consequence of that? Well, I'm thinking it's going to start speeding up, right? A force is a mass times acceleration. If it's moving to the right and you add an acceleration vector to the right, that's going to create a larger final velocity vector, right? Which is going to increase the momentum vector. Okay? And I guess what we're going to be asked is, what is the final speed? Well, let's list out. So that means our final speed is an unknown. Okay? And by the way, we have a period of time that the rocket engine is on for 5 seconds, right? So here's what we're given. We're given a mass, and that should be 500 kilograms. And we're going to be given an initial velocity of 20 meters per second. It's very fast. We're given an initial force of 1,000 newtons over the period of time of 5 seconds. Okay, and we're going to be asked what is our final velocity. Well, what I'm going to do is I'm going to draw out my momentum bar chart. If you're not supplied a momentum bar chart, just create one yourself, right? And so here is the initial momentum, okay? And here is the J vector, okay? And that's going to be equal to the final momentum, okay? And so we're going to draw this as the 0. Here's the J vector, so here's where the bars for the J vector will go. Okay, so let's go ahead and fill that bar chart up. Okay, so the initial momentum, let's say it's got one block of initial momentum. And then it's going to have a thrust added to that. And let's say that is going to be 2 blocks of thrust. Okay? So the initial momentum plus the final momentum, right? The initial momentum is positive, right? The J vector is going to be positive because it is the force vector. The force is going to be to the right and positive, so the J vector is going to be to the right and positive. So what that means is that 1 block plus 2 blocks is going to be equal to 3 blocks, right? I probably shouldn't fill those in. In fact, I'm going to correct that right now on this guy. Okay. That means this guy is going to be 1 block here. So what does that mean? Well, that means the final momentum is going to be larger than the initial momentum because the initial momentum plus the J vector is a final momentum. So initial momentum plus the J vector is equal to the final momentum, right? And the initial momentum is mvi plus the J vector, which is going to be force times delta t, and everything is positive here, right? The initial velocity is positive, and then that's going to be equal to the final velocity, which is probably going to be positive too. So we're going to divide the mass by both sides. And that's going to be equal to the final velocity. Well, the initial mass is 500 kilograms. And the initial velocity is 20 meters per second. So that's going to be 100. Plus the initial force, that force of thrust is 1,000 newtons, which is huge. And that's over a period of time of 5 seconds, right? And again, divided by the mass. Okay? So this is 100. And this is going to be 5,000 kilogram meter per second. So that'll be 5,100 divided by 5,100 divided, or 5,100 kilogram meters per second divided by a kilogram. Wait a minute, that's not 100, that's 10,000. Oh boy, I'm gonna have to rewrite that. I'll double check my math. 500 times 20 is 10,000. Woo, that freaked me out for a second. Okay, so this is 10 10,000 kilogram meter per second plus 5,000 kilogram meters per second divided by 500. So 15,000 divided by 500. Okay? So let's do that. 15,000 divided by 500. So 30. So it's 15,000 kilogram meters per second plus divided by 500. So that'll be 30. Come on, 30 meters per second. So that's how to do a problem using everything that we've learned. Okay? So here's another type of an example where you're given a problem where you have a 100 gram rubber ball, which is 0.1 kilograms rubber ball, and it's dropped from a height of 2 meters onto a hard floor. Okay, and to the right shows you basically it shows you force versus time. So this is the J vector, right? And it says how high does a ball bounce? Okay, so this is a very complex problem. Very cool. I like it. So a ball is being dropped onto the floor, and they give you this as the impulse, right? And we've learned earlier that if they give you a force versus time impulse, the area under the curve is the actual J vector, right? J is equal to F dt, right? And that is the area under the curve. Well, in this case, the area is going to be a triangle, right? And so the area is going to be 1/2 the base times the height. Let me erase that J. And note that this is in milliseconds. So 1, 2, so that's 0.08 seconds is that delta T, right? So the base is 0.08. The height is 300, right? So the area of this is going to be 300 newtons times the base, which is 0.08 seconds. And all of this divided by 2, okay? So what is that, 300? 300 times 0.08 divided by 2, so that's 12. So the area of this is equal to 12 Newton seconds, which is actually a kilogram meter per second. So in this case, the area under the curve is 12 kilograms meters per second. If you're ever given a graph like this, try to get the area really quick. Just get the area of force versus time. That area under that, it'll probably be in the form of a square or a triangle. They'll ask you to get the area under the curve if they give you this. That's what they're really asking you to do, right? So far we could adjust what we're given now. We have an impulse of 12 kilogram meter per second. We have a mass, a ball mass, 0.1 kilograms, and it starts from a height of 2 meters up. And they're asking how high does the ball bounce? Well, this part is going to take care of the bounce. We have to figure out what the initial velocity is right before it hits the ground. Well, how are we going to do that, right? Well, let's model this, okay? So you got a ball up here, and it's a height 2 meters up, right? Well, isn't that a full pie chart of potential energy? And then as this thing falls from a height of 2 meters, and that's h equals 2 meters, that ball is going to hit the ground, okay? And right as it's kissing the ground, all that potential energy due to gravity that we learned from the last chapter, this 2 meters, is going to turn to kinetic at a height of 0 meters, right? So mgh is going to be equal to 1/2 mv squared, right? And that's actually going to be the velocity right before the impact, right? So the masses cancel out. You got 2gh equals the velocity. So the square root of 2gh is equal to the velocity. Let's just call, so I was going to say let's just call g 9.8 meters per second. And that's a height of 2 meters. And so that is equal to our velocity, right? So what is that? 4 times 9.8. 4 times 9.8. And we're going to square root that number. Okay? I need to find my square root function on here. I'm going to take that to the 1/2 power, so that is 6.26 meters per second. So this is, velocity is 6.26 meters per second. Okay, well now we got it. So let's list out what we have now, okay? All right. We have a mass, which is 0.1 kilograms. Okay, it was dropped from a height and of 2 meters, and thus right before hitting the ground we found out that it was hitting the ground with 6.26 meters per second. Okay, after it hits the ground, okay, so now it's going to hit the ground and it's going to bounce, and that means its final velocity is going to go up, and now that kinetic energy is going to all be changed to potential energy to some unknown height. Okay? Okay? So it was incoming in, it was hitting the ground at this velocity right here. Okay? 6.26. So that's actually like the initial velocity before the impact. After the impact, which is governed by the J vector, which we determined was 12 kilogram meter per second. That's going to cause an upward force, and thus it's going to cause an upward J vector, right? And that's going to cause it to have a velocity downward, upwards, right? The initial velocity would have been downwards, right? Anyways, it's going to have a final velocity, and that final velocity is going to then be a kinetic energy, and which is then going to turn into a potential energy. Okay? So let's go ahead and let's model the impact, right? So the impact, again, the ball is going to have a negative initial velocity, right? And the ball is then going to be bouncing with a, let me get more room here. it's going to have, the ball had a negative initial velocity, right? And then it then hits the ground, and that should be a negative guy over here. The initial velocity is going to be negative, and that's what we found using the kinetic energy, potential energy. So now there's going to be a force upwards, which is then going to just be a j vector, right? Upwards. So we're going to be adding that, and that's going to turn into the ball bouncing and having ball bouncing on the ground. And now it's going to be moving upwards with a final velocity. Well, I'm going to turn this into a bar chart, right? So it's going to have a block, one block of negative potential, right? So it's going to have a negative, and actually put the labels above this. So it's going to have a negative initial momentum. The j vector is going to be, I'm going to give this, and this is just subjective, but I'm going to say it's going to be a big force. So it's going to send it upwards. And actually, let me do this. Let me give it 2 blocks here. And then the j vector is going to send it upwards. Okay. And let's just say this is a big force. So it's 3 blocks up. So that's going to be a positive j vector. And so you got 3 blocks. You got a negative 2 blocks plus 3 blocks. Well, that's going to be equal to a positive 1 block for the positive final momentum. Okay? Well, equation-wise, this is going to work out to a negative initial momentum, and it's negative because that velocity is negative, plus the j vector, which is going to be equal to the final momentum. Okay? So that is going to be m times negative v initial. That's our negative initial momentum, is that guy right there, plus our j vector is equal to mv final, right? I forgot to list our j vector, which was upwards, which was 12 kilograms meters per second. We got it from the area under the curve. Or that's also a Newton second, by the way. And this is 0.1 kilograms. Okay. So I'm going to divide both sides by the mass, because we're going to need that final velocity, because that's going to give us our kinetic energy. Okay. So I'm going to divide both sides by that mass, and here's what we have. Okay. And now I'm going to put in our numbers, right? Because we're going to need, basically, we need the final momentum. Okay, this is our unknown. And if we have that final momentum, we're going to get the kinetic energy from that, which will be the height, right? Right. So 1/2 mv final squared is going to be equal to mgh, right? So v final squared over g is going to be equal to h, and this is over 2g, by the way. So that's what we're trying to find. Cool. Well, this is negative 0.1 kilograms times 12, and that's kilograms meters per second, divided by, That 12 is not our initial velocity coming in. That initial velocity coming in is actually negative 6. So it's negative 6.26 meters per second plus our j vector, which is 12 kilograms meters per second, divided by the mass, which is 0.1 kilograms. And that is our final velocity. Okay? So they're doing the same thing. They're mapping out the impulse. They gave different proportions of their momentums, but it's very similar to ours. And notice that they're now going ahead and getting the ball's velocity right before impact, right? So it dropped down, and they found out it also was negative 6.26 meters per second. Okay. And so what they're saying this is using that. So when they did that, they did what we did math-wise, and they found out the velocity leaving after the impact, okay, would be 5.74 meters per second, okay. And so what they're going to do, so now in this part, they're saying now the ball has rebounded, and that's what our, by the way, this is, I should have wrote that, our final velocity is 5.74 meters per second, okay. And so now the ball is now rebounded at 5.74 meters per second, which means it's going to have a kinetic energy, which is going to then change to a potential energy, right, at some height that we don't know. So here it's got a height of 0. So now we have a kinetic energy, which is 1/2 mv final squared, and that's 5.74, which is equal to mgh, right? This equals this, that's conservation of energy. And the masses cancel out. Multiply, we'll divide both sides by g, and this is what you get, over 2g, and that's our h, and that is what they're having here, and it works out to be 2.68 meters, right? So it'll bounce back. So the interesting thing is it lost a little bit. So it bounces back less than its initial height, right? It was dropped from 2 meters, and it bounced back with to a height at 1.68 meters. And that's because this is a realistic problem. It's going to lose energy when it hits the ground, right? That ball is going to hit the ground, and it's going to make a sound, and sounds are friction, essentially. So here is basically the introduction to momentum. Okay, so what I want you to do is I want you to go ahead and do your homework problems, do your sapling homework problems, do the tutorials, and do the lab, and then come and take the end of activity quiz at the end of all that. Okay, I hope you enjoyed this. Thank you.